Today we're going to take a look at the binomial theorem, which is actually used in other courses as well. You may have actually done it in functions or even grade 11. The one thing though that you may have skipped over is where a few of the numbers came from, or at least the details of how you found them. So what we're going to do is just take a look at a bunch of binomials. So I'm going to use a generic a plus b, but this works for any binomial. And I'm going to put it to different exponents. So I'm going to go through 0 to 4. I could keep going if we wanted to. It just becomes a little bit more time consuming and lengthy to write out. But for our purposes, this is good enough. So let's actually manually find what each of these is. The good news is the first three are pretty straightforward. A plus b to the exponent 0. Well, anything to the exponent 0 is just 1, regardless of what a and b are. The second one, a plus b to the exponent 1, that's just a plus b. If only all lessons were this simple. A plus b squared. I'm just going to kind of do that off to the side here. A plus b times a plus b. If you expand that out and collect like terms, I think we can probably skip the step of showing that we have a squared plus ab plus ba, and I'll just write down 2ab plus b squared, just because that's one that we'll probably have done many times in your mathematical past. So a squared plus 2ab plus b squared. Okay, now if I want to do a plus b cubed, this is where it gets a little bit more tedious. So the way that I have to do that is a plus b times a plus b squared, which luckily we already have that. And then I'm going to expand that one out, collect like terms, and see what happens. So a plus b, a times a squared is a cubed, plus 2a squared b plus ab squared plus ba squared plus 2ab squared plus b cubed. And if it took you a little longer to do that, that's okay. Not a big deal. If I collect those like terms though, I'm going to get an a cubed, 2a squared b, and another a squared b, despite the fact that they're in the other order, but it's still multiplication, so they're the same thing. So there's 3a squared b's, and then we have an ab squared and two more ab squareds, 3ab squared, and finally b cubed. A cubed plus 3a squared b plus 3ab squared plus b cubed. Now, if I asked you to find out a plus b to the exponent 4 manually, could you do it? The answer is sure you could. We've got a couple of options. We could take our a plus b cubed that we just got and multiply it by another a plus b. We could take the a plus b squared that we got and square it, multiply it by itself. If you would like to try it, you're more than welcome to. But if I do it separately, I think what I'm going to end up getting is a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. Okay, that looks like a mouthful there. That's a lot to write out. Before I get to the binomial theorem though, itself, which is actually an equation, I'm going to make some observations. If I look at the numbers, the coefficients in front of terms, I'm going to actually switch back colors for 1 second. Anytime a term has no coefficient, it's assumed to be a 1. So for instance, a plus b is really 1a plus 1b. So these are all 1a's, or 1a to some power. And if I just underline those numbers and I read them out, we have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Hopefully you're going to recognize those particular numbers. Those are just numbers from Pascal's triangle, not a coincidence. Moreover, not only are they from Pascal's triangle, they're all combinations. That's going to help us write this out as a general formula. Also, I'm going to point out the pattern in a few of the other things. So let's take a look at the a's. In the top one, we have a to the exponent 0 because it's not there. Here we have a, which, by the way, starts off with an exponent of 1, which is the exponent that we have there. A plus b squared, well, squared starts off with a square and then an exponent of 1 and then an exponent of 0. It's not there. And then the a's go 3, 2, 1, 0, 4, 3, 2, 1, 0. So the exponent on a's are essentially the number on the bracket, the number on the binomial, the power, and they start off at its maximum value and just count down. And then the b's start off at their minimum value of 0 and count up. This one has no b's. This one has no b's and then 1b. No b's, 1b, 2b's. No b's, 1b, 2b's, 3b's. None, 1, 2, 3, 4. And that's the pattern that we want to use to be able to come up with the expansion of any binomial to any exponent. If we know Pascal's triangle and we can count up to the exponent, we can write this thing out. So this is the binomial theorem written as a formula. And while it may look a little nasty, all it's saying is that a plus b to the exponent n can be written as a summation. A summation from 0 to n where we have 3 parts. Pascal's triangle part, or a combination, n choose 0 and then n choose 1 and then n choose 2 up to n choose n. A to the exponent n minus I, so a is going to start off with an exponent of n and work its way down to n minus n, which is 0. And b is going to start off with a 0 and work its way up to an exponent of n. So what we just said is actually what's happening in that formula. So again, it shouldn't be about memorization, it should be about understanding. It's a sum of 3 things: Pascal's triangle number, a to some exponent, b to some exponent. Okay, so example 2 is repeat example 1 using the equation. We actually did the last one that way, so I think we're good to go there. Let's use that to expand x plus 2 to the exponent 5. So here's what I'm going to do. First thing I need is Pascal's triangle. Now, if I really had a big number there, like if this was a plus b to the exponent 17, and I didn't want to make 17 rows of Pascal's triangle, I would just actually do 17 choose 0, and then 17 choose 1, and 17 choose 2, and 17 choose 3 as my coefficients. But when it's this short, I can say 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And by the way, the second number in Pascal's triangle, if I'm reading left to right, is which one I'm on. So the 5th row is the row starting with 1, 5. The first row, I should be careful how I say this. The top row is 1 followed by a 0 because there's no other thing there. That's the 0th row. And then 1st, 2nd, 3rd, 4th, and 5th. So if I want to expand that out, here's how I'm going to write it, just to speed things up. So bear with me because it's not necessarily the prettiest way to write it, but it's the fastest way to think about it. Our numbers are the ones from Pascal's triangle, the 1, 5, 10, 10, 5, 1. So I'm going to leave some space. 1, 5, 10, 10, 5, 1. And now I'm going to start off with the first term in my binomial, which is an x, and it's going to start off with its maximum exponent. So it's going to be x to the 5, x to the 4, x3, x2, x to the 1, and x to the 0, which I don't bother writing. And then my second term, the 2, starts off with an exponent of 0 in the first term, which I'm not going to write because 2 to the 0 is just 1. And then 2, and then 2 squared, 2 cubed, 2 to the 4th, and 2 to the 5th. So my second term starts off with an exponent of 0 and the exponent counts up. And now that I've written it that way, I can simplify it just a little wee bit. The first term is x to the fifth. 5 times x to the fourth times 2 is 10x to the fourth. The next one is 10 times 4, so 40x cubed. The next one is 10 times 2 cubed is 8, so that's 80x squared. 5 times 16 is 80x. And the last term is 2 to the fifth, or 32. So you got to admit that that seems a lot faster than having to do this one manually by first squaring it and then multiplying that by x plus 2 again, then multiplying that by x plus 2 again, and then multiplying that by x plus 2 again, and trying to get some nasty thing that looks like this. We don't want that. So we now have a real great shortcut to take to be able to expand binomials. All right. Sometimes when we're doing these, we don't need every single term. We don't need to add up all this. So this one, for instance, anything to the exponent 5 is going to have 6 terms in it, a 0th term, and then first, second, third, fourth, fifth. Sometimes we only care about one of the terms. And so we're going to use this formula. Now this is basically the exact same thing as we had above, except it's got an R instead of an I, because we're doing just a single term and not a summation. Summations have i's in them for the index of summations. This one's just going to have an r in it. And you'll notice it starts off with term r plus 1. And the reason for that is because the first term, the one on the left, is actually got a r of 0. So when we plug in 0, we get our first term. Okay, so let's see if we can figure this out. If, for example, we only wanted the 8th term in the expansion of x squared minus 5 to the exponent 11, if we wanted the whole thing, that would have to be 12 terms that we'd expand out. It's kind of large, but we can actually simplify our lives quite a bit. And we can just say the 8th term. And I'm going to point out that I do this little thing here just to be really clear about what it is I'm writing. This means, I said, oh, come back. I'm going to get rid of that for a second. I don't like writing in crayon. I'm going to remind myself that for the 8th term there, r equals 7. I'm going to remind myself that r equals 7 because it's term r plus 1. So term 8 is r equals 7. Now that I've made that little note so that I don't make any errors, this should just be equal to n choose r. Well, the n is the exponent, so the 11. So that's 11 choose 7. And then my first term, which is x squared, to the exponent n minus r. So 11 minus 7, that's 4. And my second term, which is actually minus 5, not just 5, but minus 5, to the exponent r, and again, r is 7. Okay, so you can see how long this term is going to be. It's a good thing we didn't have to do all 12 of them. 11 choose 7 is 330. X squared to the fourth is x to the 8th. And negative 5 to the exponent 7 is negative 78,125. So now I can just multiply those numbers out. So 330 times the negative 78,125 gives us, oh my, negative 25,781,250 x to the exponent 8. Okay, so that's what the 8th term is. It took us a little bit of time to plug that all in. It's a lot easier than doing all 12 terms and then just underlining the eighth one and saying there, that's the value of the eighth. Example 5 is a little bit different. Here, instead of finding out, what is the, I don't know, seventh, eighth term, whatever, in the expansion of that, it's asking us which one in the expansion contains x to the exponent 21. I'm going to show you kind of a cool way of solving this one. Um, there are other ways of doing it. Some of them are shortcuts compared to the method I'm going to do, but they kind of bypass the cool factor or the problem solving factor that I'd like to look at. So if you figure out the others on your own and you care to use them, you're welcome to do so, but I'm not actually going to demonstrate them. Okay, so here's what I'm going to do. We have our equation that term r plus 1 equals n choose r, a to the n minus r, b to the r. So that's our generic equation. I'm now going to fill in the values that we know, since I know that this is a, that's b, and that's n, the 13. So unfortunately, I don't know what the r plus first term is, but actually I do know something about it. So rather than rewrite it, what I'm going to do is say, I know that it contains an x to the exponent 21. So it's going to be some coefficient times x to the 21. I don't know what that coefficient is. I'm going to choose a variable. I don't know why, but I choose the variable k. So kx to the 21. That is going to be my r plus first term, and the coefficient of it is going to be that k itself. Now, I do know n is n is 13. I unfortunately don't know what r is, so r stays as a variable. I know that a is equal to x cubed, and I know that its exponent is going to be n minus r, so 13 minus r. And I know that b is 2x, and I know its exponent is going to be r. So here's an interesting problem. In math, you've always been told that you can solve one equation with a variable, or you can solve two variables if you have two equations, or three variables with three equations. Well, here we have one equation. X actually, we're not, it is a variable, but we're not trying to solve for it. We're just leaving it in. But we need to solve k and r with one equation. So we need to solve one equation for two unknowns. And up till now, you've kind of been told that that can't be done. And I'm not going to say cheat, we're just going to use a neat little mathematical trick to try and figure out how to do this one. So what I'm going to note here, and yeah, actually, rather than switching color back constantly, what I'm going to do is I'm going to point out that this side here has a constant and an x to an exponent part. And I'm just going to underline the constant and the x to the exponent part. On the right-hand side, 13 choose r is a constant. It's a number. It doesn't have an x to anything in it. This part here is x to some exponent. And the last one is kind of both at the moment. So what I'm going to do is actually try to separate it out. So 2x to the exponent r is actually equal to 2 to the r times x to the r. And I'm going to bring that 2 to the r to the front. And now I can say we have a number part and a number part. And then I still have the x to the, I'm going to use my exponent rule for that middle part. So x cubed to the 13 minus r is x to the 39 minus 3r. And then that end part still gives me an x to the r. And now this is all exponent-y stuff. So now both sides look a little bit similar. There's a constant part or a number part, and there's an x to the exponent part. One more step, I think, just to clean up stuff a little bit. I can't do much with this. That stays 13 choose r times 2 to the r. But I'm taking two powers with the same base of x. I can add the exponents. So this becomes x to the exponent 39 minus 3r plus r, which is 39 minus 2r. And again, a reminder, number stuff, x to the exponent stuff. Now, the important thing to get here is that no amount of manipulation of the number stuff is ever going to introduce or take away x's, and no amount of exponents on x are ever going to change the coefficient. So now I actually do have two equations that I can look at. I'm going to look at the squiggly part, which is x to the 21 equals x to the 39 minus 2r. And if both of those have the same exponent on them, because both sides of the equation are equal, then that means that 21 equals 39 minus 2r. 2r equals 39 minus 21, which is 18, which means r equals 9. Okay, that's nice, but it doesn't actually answer the question of what is our coefficient. However, the coefficient part says that the k must equal 2 to the r, 13 choose r. And since we just solved for r equals 9, k equals 2 to the 9, 13 choose 9. Here's where we pull out our calculator. I'm going to do 13 choose 9 first, and that gives me 715 times 2 to the exponent 9, and that gives me a grand total of 366,080. And since that's the coefficient of my term containing x to the 21, I have answered the problem. So just to quickly recap what we did there is we wrote out the generic equation, we plugged in what we could, and we said that the term containing x to the 21 is some constant times x to the 21. And then we purposely separated the number stuff from the x to the exponent stuff, which gave us two separate equations. The exponents on the x on both sides have to be set equal to each other. That gives us r. And then the constants just equal to what we had as the number part, and we now know the r value to plug into it. Please do be careful on a test if I ask a question like this, because I could ask a very, very similar question, but in a few different ways. So I could, like I did here, say what is the coefficient of the term that contains x to the 21, in which case our answer is k. I could ask what is the term containing x to the 21, which is actually 366,080 x to the 21, not just the coefficient, but the whole term itself. Or I could ask, what is the term number of the term containing x to the 21, in which case the answer is 10, since the term number was r plus 1, and we found out that r was 9. So just be careful you know what it is you're trying to answer at the end, instead of just being so happy that you've done the math that you forgot what you were doing with it. All right, that's it for the binomial theorem as far as material like to teach goes. The rest of the tricks you're going to see are in the homework, so you're going to have to go find them there. Let me know if I can help you in any way, if you're really stuck on something, and otherwise I will see you in the next lesson, which is actually the next unit. So have a great day. Bye.